Next, we have Jorge Alves. I'm quite sure I've mispronounced your first name, Jorge. Exploration Technology Engineer from ISA. Are you on the line? Can't quite hear you, but when we do, I hope you can help me with your first name pronunciation. I believe it's Portuguese.
Hello. Good day.
Hello. Hello. So do tell us the correct Portuguese pronunciation of your name, please.
Thank you for the introduction. My name is Jorge Alves. It is a pleasure to be here. And thank you for the distinguished keynote speakers and for the audience and for the organization. It would be my pleasure to present to you the work of the International Space Exploration and Coordination Group and its technology working group, in particular addressing the ISRU gap assessment topic. Before I do that, I would like to confirm that the slides are being loaded by myself or by someone else. And in that case, if I try to share myself, please let me know if you do see it.
Yes, we can see the slides.
Okay, perfect. In that case, I'll cancel this. Okay, so perfect. There's a bit of a lag, but I will then proceed to indeed say that this exercise was organized by the International Space Exploration Coordination Group, its technology working group, and in particular, we did a gap assessment in the topic of in situ research utilization. The subject matter expert, co-chair of this topic is Jerry Sanders. He was mentioned before. He is worldwide known by his experience and expertise in the topic of ISRU. And I was helping him as a co-chair from the technology working group running this work collaborative effort. So next page, please. So as an initial introduction, how we approach this topic, indeed, what are the initial goals and methodology? We identify what are the key technology and the tasks and the questions that we want to address as part of the global exploration roadmap architecture. We confirm that the gap analysis is necessary in order to indeed identify the gaps and the possible solutions for closure. And we think this type of exercise can identify potential partnerships and collaboration opportunities at agency level. And that's why we decide to do this. Please, next slide. So the key objectives, what we asked ourselves was, what are the expected benefits of ISRU in the sustainable exploration landscape? What type of elements need to be infused or adapted in the architectures of the global exploration roadmap, and what specific technologies are seen as drivers for enabling this sustainability in the architecture landscape? As in particular, key objectives that we had as a starting point were indeed the resources. How can we enable these resources that can be oxygen or derivatives of oxygen, of water like oxygen and hydrogen? How can we make these products complementary for life support systems, for energy storage systems, for space or surface transportation systems? And we also start to ask ourselves, shall we start with these resources being provided from Earth, and then keep in mind how can we have a hub and spoke architecture into infusing these new resources into the architectures? How can we infuse the propellants, the reactants, the consumables into the new architecture, having started by, let's say, a configuration that was not counting with them from the beginning? So how can we adapt that in a swiftly manner? Next slide, please. So this is the team dynamics and timeline. We had already identified the two co-chairs. 12 space agencies contributed to this worldwide effort, including 4 governmental agencies involved. We are counting about 45 colleagues involved, and we have had bi-weekly telecons that started roughly 2 years ago. So this is a long-term effort, and indeed we have had a special situation during the last year in confinement, in the pandemic situation. And so we went through and we had managed to have 2 face-to-face meetings before that all started. So in October 2019, we met in Luxembourg, exactly where we are today. And in February 2020, we met in Houston. So through these face-to-face meetings, we managed indeed to strengthen not only the relationships, but also to advance the work with more fruitful discussions, with more ad hoc discussions, and indeed to understand each other's thinking and challenges, and how can we advance together. So you can see the timeline was a bit of a marathon. But at the end, we are here at the end. We are very proud and very thankful that we could do this exercise, and we hope that this could be the foundation for future discussions in this topic. So I will present to you the next slide, the outcome of the work. Next slide, please. We produced a report. You can see the report has 125 pages. In this slide, I will only present some pieces of it. So I will start by giving you a brief overview of what are the resources of ISRU, what the strategic knowledge gaps we attempted to address. We defined taxonomy and functional flow diagrams. We as well try to map ISRU in the Moon and Mars human exploration scenarios, in particular in the exploration phases of the Artemis program and in the ISRU objectives within that possible infusion in the program. We try to map as well ISRU resources, products, and applications. This is a very important aspect of mapping a criticality and timeline of these ISRU implications. In the report, you will see, but not here in these slides, we done a technology assessment per agency, per country, as well as a test facility assessment and a regulatory simulant assessment in terms of capability. This will help to understand where are the strengths and then the challenges from each country and which area are each country focused or each agency focusing on, and it will help to open the dialogue for potential partnerships. We then moved into performing a gap assessment of the ISRU, identifying cross-cutting challenges, describing a little bit how we move from ground development into the path to flight using ISRU systems, dwelling on partnership opportunities, and a little bit at the end of the report, you will find information about how do we enforce and we encourage that private sector is involved in this topic, because indeed there's a lot of capabilities that come from the mining industry that can be beneficial, and we can do spinning, and it can be beneficial for both sectors. Policy and regulatory challenges I just briefly touched upon, and the key findings will be presented to you as well here in this presentation. Next slide, please. I think the image is stopped. Can you hear me?
Can you hear me?
Yes, I can hear you.
Yes, we can hear you too, very clearly.
Okay, the slide has not moved, so perhaps I can use my offline version and stop this. In order to save time, I will do that. Okay, so through the presentation, you'll find that indeed we start talking about what are the ISRU overview. So we have divided in three primary areas in the report: in situ propellant consumable production, this first area, in situ construction, another area, and the third area, in situ manufacturing. And we have a diagram that unfortunately we cannot see it on the screen, but in this diagram you see that there is the interrelation between in situ construction, in situ manufacturing, and in situ propellant and consumable production, and how they interrelate itself or themselves within technologies, within systems, and within products in the architecture. The following slide, slide 7, it will be showing information about the expected content of lunar regolith and the expected content on polar water volatiles. And we can see that in terms of regolith, we have information about a higher 40% oxygen by mass in lunar regolith. So in particular, regolith in the highland in the polar regions has higher than 75% anorthite and iron poor. So in terms of resources, we consider that lunar regolith can be very interesting for extracting oxygen. While in terms of the polar resources, polar water volatiles, thanks to the investigations done by LCROSS, we know that an estimation of 5.5% of water can be found in concentration. I will move to the next slide. The next slide is, oh yeah, now I can see that you can all see the slides as well. So please, next slide. We're talking about strategic knowledge gaps. Perhaps it's picking up the pace.
George, the slide is there, strategic knowledge gaps. We can see it.
Okay, I just don't see it myself. So I go back to my offline version. Apologies. So strategic knowledge gap. Indeed, we start by reviewing the work of the League, of the Lunar Exploration and Analysis Group that reviewed strategic knowledge gaps, and they had a special action team that indeed identified 3 different teams. In the ISRU gap assessment team, we focus in 2 of these teams. Team 1, understanding the lunar resource potential, and Team 3, understand how to work and live on the lunar surface. And using those 2 themes and the knowledge gaps identified by that team, we have mapped what are the gaps we would like to map against our functions, so the ISRU functions. So we have identified 5 major functions and products, being polar water and polar volatile is the first one, solar wind volatile is the second one, oxygen from regolith, the third one, construction and manufacturing, the fourth one, and the fifth one, and overarching one, ISRU operations, which means is an area that includes all the others, that is interconnecting all the others. So after listing the strategic knowledge gaps, we have performed a breakdown or narrative of what the gap means. We have mapped this gap in terms of impact and in terms of timeline in the architecture, and we have also interlinked the categorization of these knowledge gaps within the architecture. You'll see in the following slides, we have an architecture definition with specific objectives, and we interlinked each of these knowledge gaps precisely with the objectives of the architecture. The next slide is talking about the ISRU taxonomy. Indeed, I have already broken down what are the 3 main elements. The first element is propellant, reactants, and consumables. The second element is manufacturing, and the third element is construction. You can see how we could break down in terms of essentially a work breakdown structure, what are the elements and sub-elements within these 3 main categories that allow us to then categorize in terms of technology, in terms of subsystem, in terms of need and knowledge gap, essentially, what are the all contributors for these 3 main ISRU categorizations. The next slide is on the ISRU functional flow diagram. Indeed, we need to understand how these pieces fit together. This looks like a rather complex diagram, but once you go through the flow, you will understand how it is interlinked, and indeed, we have interlinks here among different applications like life support and habitation systems. Like to start with, I should have said the destination reconnaissance and resource assessment, but how this then flows into life support habitation systems, how it flows into in-situ construction and manufacturing, the resource acquisition and preparation itself before extracting the resource, and the products that can be stored before utilization. So this type of flow diagram is very useful as a functional block diagram and can lead to different modularization interfaces and requirements that can be found critical and how to best tackle each one of them. The next slide indeed talks about how the International Architecture Working Group and the Technology Working Group within this ISRU gap assessment, we work together to define ground rules and assumptions, meaning objectives. How can we define the ISRU involvement in the human lunar exploration architecture, which, as we all know, is divided in 3 phases: boots on the moon, build up to sustainability, and sustainable exploration. In the first phase, indeed, we are talking about prospecting, identifying the resources and demonstrating that we can characterize those resources. While in phase 2, we move into demonstration and small-scale production, so to verify elements and integrated capabilities, to prove sustainable operations, to produce the ISRU products for non-mission critical applications. And the third phase, indeed, is large-scale production. So how can we support the crew and reusable lander vehicles towards the sustainability? How can we produce the propellants and consumables needed for missions on the moon and beyond the moon? And originally, we did not thought of performing an ISRU gap assessment for Mars, but in the end, we did define a notional ISRU human mass exploration reference architecture in order to be able to map, indeed, precisely the same capabilities and to try to map how we move from resources to products and to applications when we talk about Mars ISRU. So there's a little bit of information on Mars that is already opening the door for the next exercise, but not too much in detail here. The next slide phases. The boots on the moon, indeed, we have captured 11 objectives of this phase that can be related to ISRU. We have an example on the table there where you can see the definition of the objective, the rationale for that objective, and what are the relevant strategic knowledge gaps in the last column. So we kind of map how can we infuse, not only how can we infuse ISRU in the architecture, but what are the knowledge gaps for infusing that capability. And we did the same for the other two phases. Phase 2, build up sustainability. We have identified 9 objectives in total in that. And phase 3, sustainable exploration and operations, a total of 8 objectives. The next slide is an interesting table. I hope you find it interesting as I do. It's the ISRU resources, products, and application table. This table is quite busy, but at the end, we found a way to map it in a way that could be easily read. So you go from left to the center and from the center to the bottom right. So on the left, you see resources, you see moon resources, but you also see Mars resources. And we have linked the ISRU resource to a product. The products are read in the middle row. So each of these products are what can be, let's say, produced or extracted from the indigenous resources on the moon and Mars environments. And on the right-hand side, indeed, we mapped these products linked to an application, to a user, and to a specific priority and mission phase importance. So at the end, this is going to be an exercise to be done offline. But in this table, you can see how we go from what can be found on the moon and on Mars, and what are the possible applications, and how do we need to build the products for. So in terms of gap assessment, indeed, we performed first at the top and the first sub-element level of the taxonomy, so the work breakdown structures as defined before. We reviewed the technology capture table and ground development of flight mission plans, identified top-level observation and needs. In the area of destination reconnaissance and resource assessment, we concluded that almost everyone is actually working on instruments for geotechnical and mineral chemistry characterization. To no surprise, there is strong interest in working on the subsurface ice indirect and direct characterization. There is strong interest in mobile resource exploration and autonomy, and several orbital and surface missions are under development and planned. A focus and coordination lunar resource assessment effort is needed to understand the resource amounts, the distribution, and to better plan the mining operations. As a following step, the resource acquisition, isolation, and preparation, we found that the requirements for such process are linked to resource processing techniques. And we have identified strong interest in sample excavation of granular regolith and hard icy regolith. Although there is limited work on crushing, size sorting, and mineral beneficiation, most likely due to lack of firm requirements, we do see a strong interest on the excavation of granular regolith and hard icy regolith. Limited work on mobile excavation and delivery for large-scale systems is also present at this time. The next slide is the second slide of the gap assessment. We talk about resource processing for mission consumables. The primary processes and products of interest are oxygen extracted from regolith and ice or water extracted from polar permanently shadowed regions. Even though several physical and chemical processes are well defined, these techniques require significant advancement before the incorporation into a mission demonstrator. Complementary and overlapping work on oxygen extraction and limited work on water extraction, mostly at demonstration scale. Water and carbon dioxide processing technologies for the moon and Mars were mostly related to life support or terrestrial applications, but not with the main focus on ISRU. The area of resource processing for construction and manufacturing feedstock, we have concluded that the bulk or the redefined regolith will be the main constituent for construction and manufacture until more feedstock refined is available. Metal extraction processes require generally also large amounts of power necessary for both molten regolith and molten salt electrolysis technologies or techniques. An important conclusion is indeed we need that power availability in order to conduct these processes. Resource processing to produce plastics typically require complex and multi-step methods. As with oxygen extraction from regolith, complementary and overlapping work exists on metal extraction at a demonstration scale level. And most of this work is done in the US and in Europe. The third and last slide of the gap assessment is on civil engineering and surface construction. where we see that the significant radiation shielding needs to be realized for long sustained human surface exploration activities. Specific manufacturing methods can be used as additive manufacture that present relevant performances and a flexible approach that may be limited to the architectural opportunities. So while there is significant interest in terrestrial additive manufacturing and construction development, the development for space applications have been limited and primarily under Earth ambient conditions. Most of the work is indeed focused in the US and in Europe, with an emphasis currently on additive manufacturing approaches. Brick and slab making and sintering are also under development. The last of these gap assessment elements is in space manufacturing, where we said that metals and polymers additive manufacturing techniques have been implemented or are being developed also for application in microgravity, also on the ISS. Also, subtractive manufacturing systems are currently being developed for the ISS, and some relevant techniques used for in-space manufacturing for ISRU are using regulated with selective laser sintering method or stereolithography-based additive manufacturing. I hope you can see the slide on cross-cutting challenges. These are some of the areas we identified that are cross-cutting and indeed require interdisciplinary, even more interdisciplinary developments and discussions to take place. The areas are related to power generation and storage. Indeed, we need power to perform the most demanding processes for extraction of the resources. System autonomy. It's an area where we can all recognize the advantage of operating systems that are distant from our base location, and we can do it in an effective manner and an efficient manner. Dust mitigation is probably one of the most well-known hazards and challenges on operations on lunar surface. Surface mobility and trafficability. How can we optimize the operations, and how can we optimize the mobility, identification of resources, and how can we do it in a quick manner within the environment that we are giving? We dwell some words as well in the report on the modularity and the standardization of the hardware, as well towards the end part of the value chain, the cryogenic fluid production, the management and transfer of these propellants and reactants, and as well, lastly, on life support and habitation systems. How can ISRU support life support for crew and support habitation systems? The following slide describes a bit the philosophy from ground development to path to flight. So indeed, the approach is the conservative approach, which we go from ground development to flight demonstration using ISRU systems. So this strategy incorporates this four-step approach that you can see on the flow chart. So extensive ground testing at the mission relevant scale under flight environmental conditions and analog operational conditions on ground. Moving forward to direct measurement of resources and demonstration of critical technologies in flight, but still at the subscale level and subsystem level. While the third step, we aim to demonstrate and validate ISRU systems and products at relevant mission scale, and also in the view of a pilot system, so pilot system operations to enhance robotic and crew missions. While the last step is indeed the flight operational mission, the utilization of ISRU systems and products in a mission critical role. Partnerships opportunities, some words on this topic is indeed, we see broader involvement and partnerships with other government agencies is growing to ensure the government can maximize their investments in space and terrestrial technology development. These are important because due to the scope of work, sometimes the limitations in funding or technical issues, I think cooperating and partnering can bring a lot of advantages if we all can benefit from each other's strengths. Indeed, public and private partnerships are now more common. Recently, non-governmental organizations include industry and the private sector and academic institutions that have been increasingly participating to these activities. And the collaborative approaches to consider, they are various, but they can go from planning and coordination to sharing insight and information, coordinated research, which we are already doing, certainly specific ISRU system developments, and to joint activities and analog field testings, which I know we are also already currently doing. In the report, you will find then information from each country, each agency, information about partnership interests and activities. So the last slide is on the key findings. I will try to do it one by one so you can understand what indeed we found. Indeed, the ISRU is disruptive and requires the architectural level integrated system design approach from the start. The most significant impact ISRU has on missions and architectures is the ability to reduce launch mass. The next significant impact is the ability to extend the life of assets and reuse assets multiple times, therefore sustainability. The highest impact ISRU products that can be used early in the human lunar operations are mission consumables, such as water, oxygen, fuels, reactants, and buffer gases. A significant amount of work is underway or planned for ISRU development across all the countries' agencies involved in the study, particularly in the areas of resource assessment, robotics, mobility, oxygen extraction from regolith, as mentioned in my previous speakers. There are a limited number of large system-level facilities in existence or planned for ISRU system testing, so we have also listed those in the report. While simulants are available for development and testing, a greater quantities and higher fidelity of simulants will also be needed soon, especially for polar Highlander type regolith. A selection and use of proper simulants is critical, depending on the type of system you are simulating, for minimizing risk in development and flight operations. Several missions to begin surface and deep assessment of resources are in development, especially to obtain maps of minerals on the lunar surface topography and terrain features, or to understand the depth profile of water and volatiles on the regolith. And while there is significant interest in terrestrial additive manufacturing, construction, development, the development for space applications have been limited and primarily under Earth ambient conditions. So this will be one point to strengthen. Further research, analysis, and engagement is required to identify synergies between the terrestrial mining and ISRU, and collaboration is needed to identify and benefit from lessons learned from terrestrial innovations for harsh remote operations. The last finding, long-term, talking months or years, radiation exposure limits for crew currently do not exist. And we need them to properly evaluate the radiation shielding requirements. Once we have those, we could devise techniques and technologies and start to test them and to validate them. So the need to evaluate the Earth birth and ISRU-based shielding options is also mandatory. And this concludes my talk. I thank you for your attention and apologies for the mishaps between the PowerPoint slides. I hope you have caught everything I said. Please, I'm open to questions, and thank you again.
Thank you very much indeed, George. And yes, we do have some questions for you, quite a few, in fact. An awful lot of in-depth information there. The first question is from Adriel Amor, who is a research engineer at Sodankylä Geophysical Observatory in Finland, and asks, when will this gap assessment report be available on the ISECG website?
Okay, thank you for the question. The report is currently undergoing final review by the ISECG, International Space Exploration Coordination Group. We count that within this week the report can be final, so we hope that latest by beginning of next week we should be able to find the report there. But stay tuned, and if all goes to plan, it will be next week.
We have another question from an anonymous person. Who says, in order to understand if lunar resources are actually reserves, I agree prospecting is a critical first step. However, developing markets to understand the value of the resources is equally important for understanding reserve potential. I don't know if this is best directed to you, but the question is, how is Europe developing the full market pull for lunar resources?
Yeah, I think I catch the question from the perspective of utilization. How can we define what are the business cases and the economies that are going to use these resources? And if that is the right question, ESA indeed is thinking about it, and we are as well conducting or preparing to conduct a call for ideas on the ESA Ideas platform, where indeed we tackle exactly that question. So we know what can we expect in terms of resources. We want to make sure in terms of absolute quantities and types as well what is there, but we are also working on the other side of the value chain, on the inside, what are the business case, what are the utilization, the applications, and by identifying those, we can hopefully create the full chain, and we can identify the players on the different phases of the chain.
The anonymous person is Clive Neal. Apparently his check-in didn't work. Thank you for the question, Clive. Ricardo asks, other than chemical physical transformation infrastructure, what are the main technology bottlenecks for extracting enough resources for sustaining life on the moon? For example, rovers, drillers that can operate autonomously 24/7, maintenance-free, power production, etc.
Yes, indeed, there are 2 or 3 key technologies that need to be mastered in order to make this whole dream work, which is indeed autonomy. We need autonomous systems, robotic systems that can precisely sustain the harsh environment, the dusty environment, the low temperature environment, and can support the astronauts, the crew in the operations. But for that as well, the other key area is power. We need to have an infrastructure of power solutions that support these extraction techniques. So I would say that the robotic systems supported by the availability of power or energy, not only to operate during the lunar day, but to sustain the lunar night, are key technologies. And without the communications infrastructure, it's also clear that we will not be so efficient. So communications in terms of constellation or infrastructure is also a hugely important supporting technology.
We have a comment here rather than a question from Christophe Bosquillon, who's the founder and CEO at Autonomous Space Futures Limited. And he talks about the professional course last week, which took place, and it was led by Colorado School of Mines, ISU, and Luxembourg Space Agency. He says it's an excellent course loaded with outstanding value and provides a lot of useful frameworks, starting with space resources validation from assumed to proven reserves. So perhaps there's some information about that online. Just checking through here now, and various people are saying hello still and offering more information. So you can see all of that on the chat.